Okay, in this video we are going to learn how to run the global ionosphere thermosphere model. So the first thing that we're going to do is open terminal, and we're going to make a directory just to install it somewhere. So I like to make a directory that's called like models. And so then you go into models, and now we need to download the code, and the code is on GitHub, but I can never remember what it's called. Okay, so we're gonna go to Safari, and then we're going to go to github.com, and we're gonna actually go to the Gitum code the whatever it's called, and then we'll go into the repository that's called Gitum. And so this is Gitum code Gitum. And then we'll go up here and we will copy this link, and then we will do git clone, and we'll paste the link. And it will hopefully download the code. I've never done it on this computer, so we'll see if it works. Oh, look at that. It's downloading the code. That is fantastic. Oops, I'm going to make this a little bit bigger so you can all see what I've just done. Yeah, so we did git clone and then the web address that we got from Safari. And we can leave this open if we want. And so what I'm going to do is I'm going to look through the quick start, which tells you how to do all of these steps. So we already did this step, and then if we do an ls, you see that there is Gitum in there. And so then we can go into the Gitum directory, and then we need to configure Gitum. And so the way that we do that is you can copy and paste this if you want, or you can just type it config -install compiler equals g4tran10, and then we're going to run earth first. So the g4tran10 is the version of Fortran that we installed on the last video using port or Mac ports, and so hopefully this will work. This computer is super slow, unbelievably slow. All right, so it has configured the code, and so we should, in theory, this is the moment of truth. It's the moment of truth. You just type make, and then hopefully everything just works. And we can spread this out a bit so we can see all the things that it's doing. And then it's going to take a while to actually do the compile. The thing that is the most worrying is this line, the MPIF90. So if the MPI version and the G4tran version are incompatible, then this line doesn't work. And what this indicates that it did work, since it did work, that means the whole code will probably compile. And so we'll just sit here and wait for a few minutes, and hopefully everything will just compile. While it's finishing, let's actually figure some things about this computer. Let's go into about this Mac, and let's do system report. This has 4 processors, so 4 processors is what we need to know, and so hopefully it will work with MPI. Fantastic. And so your computer may have more or less. All right, so it's done. So it created the Gitum the Gitum executable, and that's in the source directory, but we don't really care about that. So what we're going to do is we're going to make a run directory, and the way that you do that is you just type make run dir, and that actually sets up the first run for you. So go into run, and you can see that there is a Gitum executable, and then there is this file that's called uam.in, and that is how we control the Gitum runs. And so we're going to move this out of the way here. We're going to move this here, and we're going to see what the manual says. All right, so we did the make run directory. We cd'd into run, and now are just going to go for broke and try the mpi run minus np4 getum.exe and see if it runs. And we are going to allow this. And this is great about the way that University of Michigan has set up the security. So we're just going to allow all of these things. And every single time I run the code, those show up. I am not bitter at all. All right, and then right now it's initializing the magnetic field, and that takes a little while. And now it's doing the main run. And so it reports to you like how many time steps it's taken. It reports the time that it's actually on, and then it reports the wall time, how much time it's actually taken so far. And it actually gives you a projected time. All right, so it actually just runs for 5 minutes. That's the test. And so it finished that run, which is amazing. So now if we go back to here, that's a very, very crappy resolution run. It's just a test to see that we can actually run the code. And so we can go into the UA directory, which stands for Upper Atmosphere Directory, and then we can type pgetum. So we go into UA, we do an ls, and there are a bunch of different directories in here. The data directory is where everything is output, and pgetum is the post-processing code. So we just type pgetum, and then it post-processes all the code. And now let's see if we got Python set up correctly. So we're going to go into the data directory, and then we're going to try running this script. Data. Okay, once again going for broke. Source, Python, plot model results, var equals 3, elt equals 120, and let's do the plotting at 5 minutes. Will it work? No, it doesn't work because it needs netcdf4. So it needs the netcdf things for the Python stuff. All right, so what we're going to do here is we're going to open up a new shell, and I'll blow this one up to All right, so we need to install this netcdf. So let's do port list grep -i netcdf and see what they have available in netcdf. All right, so we installed Python 3.8 on this computer in the last video. And so what we need is Python 8 netcdf4. So what we will do is we will do a sudo port install Python 3.8 netcdf4. And then we type our password. All right. So in theory, this should be able to work. Okay, so here, let's just try running it. And it worked. It gives you a lot of errors, which is fine. These errors are just warnings, and they're from matplotlib. This is because this plot model results is a really old code, and it was designed for older versions of matplotlib. It is perfectly fine. And there it is. All right, so this is plotting out the mass density rho at 121 kilometers altitude. And that was with this command here. The -var equals 3 says to use rho, and the altitude is 120. So if we were to just say -list It doesn't like the list. Okay, so I don't know how to run this, so I'm just going to use -H. And the -H actually listed all of the variables for us. So the zero variable is longitude, latitude, altitude, 3 is rho. If we wanted to put electron density, that is 34. So let's plot that. 34, and let's do this at like 350 kilometers, and we don't need the -H anymore. Okay, and then we can do open, and you can see that it made a file that's called 34 var 34. Do that, and there it is, and you can see the equatorial ionization peaks and stuff there. It was only run for 5 minutes, so this is probably just IRI still at this point. Okay, so let's try to do a different run. Okay, so I went back to our original directory, which is the Git'em directory, and now if I want to, I can type move run into run first test. And so now the run directory is called run first test. So let's talk a little bit about the UAMIN file here. So let's go into the run first test, and we can look at this Emacs UAM.in file, and we can see what's in here. All right, I'll quickly go through and explain this, and then maybe we'll do another run or two. So this basically has, the way that it's laid out is that it has these hashtag commands, like this hashtag debug, this restart, time start, time end, etc., all the way down. And it goes on for a while. And the beautiful thing about this is that it pretty much just ignores any line that doesn't have a hashtag in it. It doesn't think of these as commands at all. And so you can make copious notes in here, and that's what this has done. So it basically describes some of this stuff. The debug level basically tells you how much crap is going to be output. So if you want just a massive amount of stuff, let's actually try running it with a 10 just to see. I might not do the entire run because it's just so much. NP4. Oopsies. You really only want to see this if like something goes wrong. So I use this for debugging only. And you can change this to like 1, and then you can see a little bit more stuff. And so it tells you, some of the things that it's doing, but not as much as it did before. And so you just get different levels of verbosity, and it just, it's interesting to look at like what the code is doing, I guess. But once again, I usually only change it when I'm trying to debug something. All right, Control C, and then that kills it. Restart the code can basically be stopped, and then you can restart the code, and then you can go forward from there. I do that all the time when I want to run with different high latitude electrodynamics or something like that. I'll run, basically run 24 hours and get rid of all the beginning crap that goes on in the code. And then you stop at 24 hours, and then you start and run a real simulation. And then you could restart it at that point and run with different electrodynamics and restart it again, run with different electrodynamics. It's good for testing like the robustness of the storm response of something or something like that. The start time is year, month, day, hour, minute, second of when you want to start something. I usually start things 24 to 48 hours before like an event actually happens. The end time is just where you want the code to end. Okay, the grid is a little bit complicated. So the grid, this tells you the number of blocks that you want in both longitude and latitude. So the way that the code is set out is it's what's called a block-based domain decomposition. So it runs with different blocks. So right now the Earth is broken into 4 blocks, 2 in longitude and 2 in latitude. All right. So we run with 4 processors because 4 is 2 times 2. And so that helps define the resolution, or defines the resolution. So this says that there are 2 blocks in longitude and 2 blocks in latitude. So how big is a block? Well, a block is the number of cells that are defined in this other file that is in the source directory called mod size. And mod size tells you the number of longitudes, number of latitudes, and number of altitudes in each block. So right now we have 9 cells in longitude, 9 cells in latitude. And the website explains this a little bit more, and it gives you some examples of if you wanted to run 5 degrees by 5 degrees, what you'd have to do. Because the computer that I'm using is a really crappy iMac that was made in like 2016, it only has 4 cores. So if I wanted to run if I wanted to run with 5 degree by 5 degree resolution, I could only run it on 4 processors, and so I would have to change my mod size stuff to work right, and then I would recompile the code, and it would make those blocks a little, instead of 9 by 9 cells, it would be like 18 by 36. That would get me 5 degree by 5 degree resolution. And then the code would run very, very slowly, but I could still run it on this computer, this crappy computer. Okay, so next we want to output the log file. We're going to output every second to the log file. So the log file, if we looked in that UA data directory, there is this log file here, and it has just a lot of stuff in it. It tells you, the year, month, day, hour, minute, second, the minimum temperature, maximum temperature, mean temperature, minimum vertical velocity, etc., etc. Lots and lots of stuff from the code. So you can look through this and see basically what's happening in the code. Oops. Ram.in. Okay, save plots. There's a bunch of different plot types for GitHub. 3D all is the one that I normally use. This says to output it every 5 minutes. Most of the time when I'm running like several days, I don't output every 5 minutes. I output every like 15 minutes. So you can set the time here. Like 15 minutes is 900 seconds, like that. Here, it's set to static F10.7. I almost never use that. I almost always use dynamic F10.7. So the code comes with an F10.7 file that describes what the F10.7 was doing for the last, 60, 70, 80 years. You can use different EUV models. Right now it's just using EUVAC. Or you can use FISM. The FISM, we include many, many years of FISM data, daily average solar spectra data, and so you can run with FISM just by turning this to true. You can run with a static hemispheric power index, or you can input a hemispheric power index file. And there's an example file that comes with the code. There's a new auroral model from Chen Wu and from me, I guess. Chen Wu and me. Fang energy is basically like the energy deposition, how the aurora is deposited. Cusp, you can turn on a cusp and you can set the average energy and the energy flux, and basically as By rotates around and Bz changes, it will change the location of the cusp, but it will keep these characteristics. Auroral modifications, so what we normally do if we're running with the hemispheric power index, we can modify the aurora to basically normalize it to the actual hemispheric power. We also have done experiments where we multiply the average energy by a little bit or divide it by a little bit. We can set whether we want a kappa distribution or not. We can include ion precipitation or not. That's a sort of advanced feature, which is harder to do, and we can talk about that some other time. This is the solar wind, IMF BX, BY, BZ. We almost never use this static stuff. We almost always use this MHD indices file. If you want to turn on a dynamo, which I highly recommend that you run with a dynamo, this is the low latitude dynamo, then you basically can turn this on here, but you can only run this with higher resolution. Really, the really super crappy test run resolution is not good enough for the dynamo. Neutral heating efficiency is usually set at 5%. Photoelectron heating efficiency, I usually turn that off. This is for eddy diffusion, basically sets the eddy diffusion coefficient at 50, and then it sets the pressure levels. The tides, it's going to use EMSIS tides. GSWM, it doesn't use. Apex, it uses Apex by default. You can turn this off and then use a dipole. And then there's a bunch of stuff that you can turn off here. Like if you wanted to use, you wanted to turn nitric oxide cooling off just to see what would happen, you can turn it off here. If you wanted to turn off like viscosity, you could turn that off here. Not really recommended for doing any of this stuff unless you know really what you're doing. This use improved ion advection, leave that alone. And then the chemistry, you probably want chemistry, because if you turn off chemistry, then you basically don't have an upper atmosphere anymore. So leave that alone. Okay, so there is a very fast run through about what this UAMN file looks like. This will be a good introduction for how to run GitHub, and then if you want more information, you can look on the GitHub site, and then you can contact me directly if you would like. You can probably find me on GitHub somewhere, or you can just do a Google search for Aaron Ridley, University of Michigan, and then just email me, and I'll answer any questions that you really have. I'll probably post more videos on how to run GitHub, but hopefully this is like a good first introduction. We're going to end there, and hopefully you have learned something from this video. Thank you very much for watching.